In the last video for this chapter, I want to cover two things. First, I want to talk about how to physically implement the compensators that we now know how to find their transfer functions. Second, I want to use an example to show you very quick how to design a feedback compensator. For the compensators in the PID family, active element has to be used because of the integral or derivative operations that are involved. Here you're given with an op-amp circuit. Op-amp is an active element. This op-amp is in the inverting amplifying configuration. The transfer function of the circuit is equal to negative of the impedance on the feedback path divided by the impedance at the input. If you choose different component or a combination of components for Z1 and Z2, then the transfer function of the circuit will come out in different form. For instance, if you choose a resistor for Z1 and a series combination of a resistor and a capacitor for Z2, then the transfer function of the circuit will come out in this form, which is basically a transfer function of a PI controller. Then you can use this inverting amplifying circuit as a PI controller. If you choose a parallel combination between a resistor and a capacitor for Z1 and a resistor for Z2, then the circuit can be used as a PD controller because the transfer function of the circuit is in the same form of a PD controller. So now you know that if you have a controller in the PID family that you want to physically implement, you will start with picking the appropriate component or combination of components and then compare the desired transfer function with the symbolic expression of the transfer function provided in the table to calculate the values of the components that you need to use in the circuit. The same inverting amplifying circuit can also be used to implement a lag or lead compensator. This slide shows what combination of components you need to choose for Z1 and Z2 in order to create a transfer function that is in the same form as a lead or lag compensator. From the perspective of implementing a compensator, there is one advantage of lag-lead compensator over PID controller, which is that you can actually use passive element to implement a lag or lead compensator. On this slide, only passive elements are used to implement a lag and or a lead compensator. So this is how you can use the basic circuit components to implement the 6 compensators that we learned so far. Next, I want to talk about feedback compensator. At the very beginning of this chapter, I introduced 2 compensation techniques. One is to introduce a compensator in cascade with the plant on the forward path. That is called cascade compensation. The other compensation method is called feedback compensation, which is achieved by placing a compensator on a feedback path. Here I have an example block diagram of a system with a feedback compensator that is added to the inner loop or the minor loop. A feedback compensator works to reshape the root locus, just like the cascade compensator. It can be used to generate a faster response. One of the popular feedback compensators is called rate sensor, which I'm going to use example 9.7 to demonstrate how to design. What is shown here in the picture is the first autonomous underwater vehicle that was designed to carry out some underwater tasks. To make this vehicle submerge or rise, a pitch command needs to be applied to create a vertical force. The system block diagram given below identifies some of the key components, which has a feedback compensator called pitch rate sensor already included in the inner loop. The reason this block is called pitch rate sensor is because it actually calculates the rate at which the pitch signal changes with time because of the factor of S. The objective to be achieved by the pitch rate sensor is to reduce the settling time by a factor of 2 while continuing to operate the system with no more than 20% overshoot. So what we need to do is to find the values for K1 and K2 that will produce the desired time response. The packet provides very detailed design steps. What I'm going to do here is just to walk you through the process to give you this bigger picture of what it takes to get to the design solution. Step 1 is to reduce the system to a single loop so that we can write the open loop transfer function, which is denoted as G of S, H of S, sub F. The second step is to remove the feedback compensator and design a PD controller instead to achieve the desired time response. So this is the system without the feedback compensator. It has been reduced to the unity feedback configuration. K1 comes from the original system, so it stays. It has been chosen to be equal to 0.75 to achieve a percentage overshoot at 10%. According to the simulation, when K1 is equal to 0.75, the actual percentage overshoot is 11.8%, which is still below 20%, and the settling time is 24.4 seconds. As for designing the PD controller, we chose to achieve 10% overshoot in 6.1 second settling time, which is a quarter of the current settling time, which gives us the PD controller with a gain of 9.266 and a 0 at negative 1.413. So then we have the open loop transfer function of the system with the PD controller, which is this function right here. The next step, step 3, is to make the transfer function of the system with the PD controller that has the desired time response to be equal to the open loop transfer function of the system with the feedback compensator, which we found in step 1. And the idea here is that if these two open loop transfer functions are equal to each other, then the root locus of these two systems should be identical. Then the time response that we were able to achieve with the PD controller is expected to be achieved by the system with the feedback compensator. So by setting up equations to solve for K1 and K2, we found that these are the values that we need to use for the system with the feedback compensator. The next step, of course, is to simulate. If you take the K1 and K2 values back to this block diagram, then you can find the closed loop transfer function, and then you can use MATLAB to simulate its step response. Here's the simulated step response of the system with the feedback compensator on the same graph with the system without any compensator. The percentage overshoot of the system with the feedback compensator is 2.3%, which is well below 20%. The settling time is 14.3 seconds, which is significantly reduced from 24.4 seconds obtained from the uncompensated system. However, we were not able to reduce the settling time by a factor of 2, then we have to revise the feedback compensator. The revision starts with redesigning the PD controller with more stringent design requirements, and then we will repeat step 3 to come up with new values for K1 and K2. As you can see, designing a rate sensor, which is a type of feedback compensator, relies on designing a PD controller. There's an extra step in the end that you have to perform to manipulate the math such that you can translate the PD controller to a rate sensor's transfer function.